Hello, good afternoon. Thank you for having us today. So today we're going to talk about the state of Qubit. My name is Jean-Francois Bobier. I'm a partner and vice president at BCG.X, which is our innovation unit inside Boston Consulting Group. Qubits are very interested. We are all here for them. As you know, there are a lot of different modalities, a lot of trade-offs that are involved because it's not only about the number of qubits, it's also about the fidelities. And then when you start to look a little bit more closer, you have other factors, such as, for example, clock speed, connectivity, and many others that play to something that we'll talk about later, which is something that we heard more and more, which is time to solution. So basically, do you use a software, an hardware architecture to a solution? We published a report last year on the state of quantum computing, and we listed obviously the 5 important modalities out there. And actually, on the top 3, there were superconducting qubits with Theau, and we have neutral atoms with Yuval and Loic. So we have a chance to have the top 2 modalities out of 3 today. So I think with that, we should have a good view of the state of qubit. So maybe we'll start with maybe a roundtable with different panelists here, and then we'll ask some questions. Maybe Yuval, you can start with neutral atoms.
What is the question? I'm sorry.
Who are you? And what your company is doing?
My name is Yuval Boger. I'm Chief Commercial Officer of QuEra Computing. I apologize for not having a French accent like my friends here. And we make quantum computers using neutral atoms based in Boston, based on technology from Harvard and MIT. We have a computer that's working for 3 years now on Amazon Bracket, 256 qubits. And recently we installed a computer in Japan, a gate-based computer at AIST. And just yesterday, and maybe we'll talk about it later, we published another fantastic article, I think, in Nature about algorithmic fault tolerance, which is a way to speed up the calculation when doing error correction.
Theau?
Yes, so hi everyone, I'm Theau Peronnin, CEO and co-founder of Alice & Bob. Alice & Bob, we're doing superconducting qubits, but of a special kind, the so-called cat qubits, which are designed from the ground up for fault tolerance with a first layer of built-in error correction within it, which dramatically reduces the required overhead for error correction. The company is about 5 years old. We're based mostly in Paris with an office in Boston, Boston being the place to be, obviously. And we're about 150 at the moment, racing towards 2030 for a graphene device with 100 logical qubit made out of 2,000 cats.
Loic?
Hello everyone, Loic Henriet, CEO at Pasqal. So at Pasqal, we are also working on neutral atom-based quantum computers. So this technology originally was developed by leading labs and on both sides of the Atlantic. And there was one very strong group in Paris, in the south of Paris at Institut d'Optique, and that's from where the company span out. So at Pasqal, we are 6 years old, and we are developing and shipping neutral atom quantum processors in various HPC centers around the world. We have one machine accessible through the cloud as well on Azure Quantum Cloud, Google Cloud Platform, and we have machines deployed in France, CEA, Germany, Saudi Arabia next year, and Canada the end of the year, should be something like that. So really pushing hard to have those machines ready for industrial grade usage. I think that's one of the key challenges that we are facing as an industry, to make those machines really reliable, that users can rely on for their everyday workflow. And yeah, we are working very strongly on that, in addition to the pushing the technology, of course.
So as everybody knows, I think in the audience here, there are basically 2 important time periods that we are looking for, actually 3, but let's say just for the focus right now, 2. One is the current period until error correction, right? And it is still not, we don't have error corrected computing at scale right now. And then there will be error correction, and we hope, and we probably explain a little bit more the timeline, but around 2029, 2030. Maybe I would like to stay with Loic because it's known that Pasqal tries to make the current period work today using a different approach called analog qubits. Can you explain a little bit more what it is and why it can bring benefits today?
Yeah, of course, happy to do so. So you can either use qubits really at the low level, using the natural knobs that you have to really tune the dynamics and implement algorithms at the low level, or you can implement quantum error correction onto it. The thing is, quantum error correction for now is still rudimentary. Everyone is working very hard to make it work, but the price you have to pay is actually not worth it at the moment on most devices. So that's why we really want to use the devices and the capabilities that we have now with analog mode and really tuning the natural knobs that you have on the device to implement algorithms. It can be quite useful in problems like optimization problems or simulating dynamics of quantum systems with quantum magnetism. There are many instances of problems that are very interesting. Also, I think it's good because it puts the technology right now in the hands of end users to actually really build this industry all together, because we need usage, we need feedback from the companies that will be the heavy users of this technology, and that's one of the real value that we get from this analog computing mode. And yeah, so that's one of our focus at the moment.
Just to clarify, in analog, you don't use gates. It's a different way to program the machine, right?
Yeah, exactly. So you use like pulse level control, so the natural physical components controls that you have. Whenever you want to implement quantum error correction, you need gates. At some point, it's really necessary. And we are quite happy that actually today at Pasqal to announce that we have prepared the first logical qubits on our exact same platform. So that's one strength of neutral atoms on the same machine that we had implemented the use cases with Crédit Agricole, for example. We were able to implement quantum error detection and really road towards quantum error correction.
Maybe let's switch to superconducting and then we'll go back to Yuval to neutral atoms. So in Theau, you aim directly for logical qubits. So a lot of people in competitors to yours, like IBM, they sell machines that are NISQ devices. So why did you make that bold choice? And where do you stand in the development of those logical qubits?
Yeah, so indeed, it's quite different philosophy. I guess our roots, we all share the same end goal. We know the long-term high-impact use cases. Those are pretty well documented nowadays. Basically, they start at about 100 logical qubits with 10 to the minus 6 errors per gate for the most favorable one. But I'd say the real peloton of use cases is at a few hundreds, couple thousand logical qubits with error rate more than 10 to the minus 9 at least. So once you've said that, yeah, you have quite a lot of work to get there. And when you look at the historical approaches to quantum error correction, the size, the level of redundancy required was just enormous, gigantic. And in many approaches, that remains the case. So the philosophy in which we were born was to say there must be a clever way to do so. And this is how we started to design cat qubits. It's really to find a shortcut. That shortcut comes at a price. Cat qubits are extremely good at correcting errors, namely bit flips, which simplifies the whole stack, but they pay the price slightly on phase flips, which makes us really not good at NISQ. And so for us, it's quite an obvious choice, where we're really racing towards the end goal with a machine that is really fast, scalable, very compact, and so cost efficient as well. And in the meantime, we let the community educate itself with other modalities.
So Yuval, QuEra was the first to announce error correction on neutral atoms. It was the world first. It was published, I think, on Nature. can you explain us more where you stand on this? You just mentioned the new paper that is about to come. Where QuEra stands on error correction, and where do you see the future there?
So we believe in showing stuff, not just telling. And so that's why, just like Pasqal, our first machine was an analog machine where you can map certain problems, certainly problems with a geometrical component, into the arrangement of the atoms, and then use, for the physicists here, time-dependent Hamiltonian to make the system evolve and then measure it. That was the analog system that we launched 3 years ago. Our second generation system is a digital system. And although we have demonstrated some very high single qubit and 2 qubit gate fidelities, our focus on that system, and in general, our focus on the future, is on logical qubits, on detecting and correcting errors. And indeed, as you said, in December of 2023, we published a paper, a demonstration that was led by Harvard with participation of QuEra and MIT and NIST and University of Maryland and maybe a couple others that I forgot, that demonstrated 48 logical qubits, which I think at that time was a world record, and it probably is still a world record. So we demonstrated a system that you had 48 qubits, and we were able to detect errors and thus improve the performance. And ever since, we've been working on various aspects of that. So one aspect is to show that we can scale that system, that we can have more and more logical qubits. The other aspect was to demonstrate that we can speed up the process. One of the fantastic things about neutral atoms that both Pasqal and QuEra enjoy is that neutral atoms can move around. And so we have what's called all-to-all connectivity, or basically any qubit can interact with any other qubit. And that allows us to implement more efficient error correction methods. And so the paper that was published yesterday in Nature demonstrated that because of these capabilities and the ability to do gates in parallel and a whole bunch of other amazing stuff with neutral atoms, we're able to dramatically reduce the number of cycles that are required to run an algorithm. In fact, when you design a logical qubit, you worry about what's called the code distance. The code distance, the larger the code distance, the more resilient the logical qubit is to errors. And we were able to show a reduction of typically 30 or 50 times in the number of cycles that we have to run because of the special capabilities of logical qubits. And what that enables us to do is to dramatically shorten the time to solution, the time to execution. So there's a related paper that we published a few months ago that showed that based on this technology and based on reasonable, we think reasonable assumptions for speed, we're able to reduce the time that it takes to crack RSA 2048 from about a year before that algorithmic breakthrough to about 5 days, which makes it all of a sudden much practical. Of course, don't worry, we don't have that computer yet. It requires many more qubits than we have at the moment, but this just shows the power of neutral atoms in general in this approach.
Okay, so let's shift gears and we talk about that, but we need to revisit it. So I think when I talk to investors and also corporate, there are really two concerns that come up now that error correction is kind of considered as a given, even though it's a lot of hard work and it's not entirely there yet, but people consider, okay, it's done, right? Now they are looking at the next two things. So one is scaling. We mentioned the numbers that Theau mentioned. I think they are really there. I mean, we'll not be happy with hundreds of qubits. We'll be more happy with actually hundreds of thousands of qubits and 10 to the minus, 10 to the power of 9 gates, so billion gates, right? And we are very far from there. So every time we cross, we start to reach a threshold, there's another one in quantum. So how we scale this, and do you have confidence that you can, once you have solved that, you can do that? And then there's this question of time to solution, because another thing that investors and corporates are aware is that no modality is perfect. For example, superconducting qubits, the something called connectivity is very bad because it's a 2D circuit, and normally you can only communicate to the qubit just near you, right? But the clock speed is super fast, typically in the megahertz, but you will correct me, right? And for example, when we hear about neutral atoms, it's kind of the opposite, right? The clock speed is low, typically, you will correct me, but typically in the kilohertz range. But the connectivity is better. But maybe correct me, please.
Not there yet, actually.
Not there yet. Yeah. You aim kilohertz, right? And of course, people say, okay, what's the difference between 1 kilohertz and 1 megahertz? Well, if I tell you that so take 1 hour, for example, you multiply 1 hour by 1,000, it becomes 42 days, right? So actually, speed matters at some point, right? And I was just wondering, where do you stand on these two topics? So maybe I'll give you back the floor, Loic, on these two topics: scalability, time to solution.
Yeah, of course. Yeah, I think neutral atoms have demonstrated that it's a nice modality for scaling, relatively easy with the same scaling, the same trapping system, with the same laser system to actually have thousands, tens of thousands, maybe qubits in the same vacuum chamber, which is very, very meaningful, very powerful. There are many things that you can do with that. The clock rate is not there yet. Actually, it's not because the operations are slow. The operations are quite fast. Gate times are relatively fast. The thing is, we spend most of our time not doing computation, but actually preparing the register, measuring it, and so on. So there are various solutions to increase the clock rate, various technical solutions that are explored in many labs around the world. So there is a hope to reach kilohertz or tens of kilohertz regime, but we're not there yet. It's true that there are trade-offs everywhere, and it's important to work on those aspects. One thing that I would like to say, though, is that it's important to have the time to solution aspect, but also the quality of the solution that you output is meaningful. So quantum computers are generally good at high complexity, low input, low output problems, and it's sometimes the quality that matters most. So something that you cannot attain with classical computers. So I'd like to mitigate a bit your comment about time to solution being the most important metrics.
Same question for you, Theau. So scaling and time to solution. But how do you say this? Considering the constraints of superconducting qubits, especially around connectivity.
Yeah, I've grown a bit tired about commenting everyone's roadmap and feasibility. Now, the way I look at it is really, what does the final product looks like? And so you're talking about time to solution, and I think it's relevant. It was well caught up by NERSC report a few days ago. Also, that there is kind of a maximum duration of a computation to be humanly convenient, which is a few days, a week at most, basically. So it's the size of the problem that matters, but it's also the cost. And actually, the time to solution is a proxy for cost also in many regards, because the way you can think of is that if you're a large data center, you're going to acquire some hardware that you're going to want to use and make most of it, run a maximum number of jobs on it. And so the question of the speed is also the question of the cost per job that matters. Now, indeed, superconducting circuits who operate more in the megahertz range, meaning the typical logical clock cycle is at about a microsecond in terms of order of magnitude, with no downtime, because indeed they don't move around, so we don't have all-to-all connectivity. But here again, in the logical qubit space, there is a lot of caveats that we need to educate about. For example, the logical connectivity is very different from the physical connectivity, because once you have logical qubits, you start to do surgery lattice, you can move logical qubit around very differently. Then indeed, if you have all-to-all physical connectivity, you can gain on the a factor of the distance of the code, which gets you a good order of magnitude. But that is if you compare to the naive way of doing FTQC on superconducting or solid state, because you can do time-optimal quantum computing. I mean, you have many tricks. So at the end of the day, my feeling kind of connects with the one of Hartmut Neven from Google, which is, I think neutral atom will capture all the world first, all the way to 2030s. you're in excellent position to do so. But then when you look at commercial systems in terms of productivity, we're good with superconducting.
Maybe we can give Yuval the last comments. I would like to hear about some of the latest innovation you are bringing that are difficult. So you talked to me, for example, about the reloading of atoms, which is something that you mentioned last year as a frontier, and I think you already made progress. There are things on lasers. Can you tell us more about some of the exciting things you are doing right now?
Of course. So, by the way, this is a 40-minute panel, and we had a 20-minute clock, so we have another 20 minutes. So this is just the half of the panel.
Okay, that's good. I thought because okay.
So do I still give the last answer? It's going to be a really long one for 20 minutes, right? Yes, we also when you say time to solution, you're assuming a solution, and for a solution you need a lot of qubits. And so you start asking yourself, with other modalities, how do you get there? Can you really put 1 million superconducting qubits on a chip, or how many chips would you need if you're, say, IBM? Do you need cryogenic cooling? Is that going to take, the Stade de France size data center? Is it going to take 100 megawatts of power? Is it going to cost $1 billion? So the first thing to notice is that we have no doubt that with neutral atoms you will have a solution. Now, as Theau mentioned, there are many tricks to do speed. By the way, conceptually, you don't need to move qubits around on a neutral atom. You could just say, I have static qubits with static connectivity, and I'll just operate them as if they were a superconducting computer. Of course, we don't want to do that because we think that with moving qubits around, we can get more efficient error correction codes. We can do transversal gates. We can reduce the error rates in a lot of different ways. So it's actually a design choice. It's not an inherent limitation of the technology. But to your question, there's still open things that we have to solve, and of course they're difficult. We have a saying at QuEra, if science was easy, we'd have marketing do it, right? So science is difficult. And one of the things that happens...
You're not working in the lab yourself?
Not right now. Actually, I'm barred from the lab. One of the things that happens in neutral atoms, especially as they move, is sometimes you lose atoms. It's almost like if you drive your car super fast, you can lose the car flies off the road. So if you want to do really, really long calculations, and you measure atoms or you lose them, you have to reload them. So amazing work that was done by Harvard, with a little support from QuEra, but this is essentially Harvard work that was done, demonstrated what we show, what they call continuous reloading. So they basically had both 3,000 qubits trapped, and then sort of had a conveyor belt that continuously provided fresh new qubits and was able to load them without disturbing the others. And they actually operated that system for 2 hours. I think after 2 hours they got tired of watching it, but they could have run it forever. So this is one more step in having lots of qubits and developing compilers that would efficiently map algorithms into the special capabilities of the hardware, in improving the error rates and finding new error correction codes. So there are a lot of things that we still have to do, but in our estimate, 100 logical qubits or several hundred logical qubits would come much sooner than 2030.
Which is good news for the industry, obviously. Theau, I would like to ask you also the same question. So what are the current research topics that you are working on? I know, for example, fabrication is still much an issue. The job have the right perfect Josephson function junctions that are exactly the same in a chip or things like that. What are the problems that keep you at night right now?
The problems that keeps me at night are not technical. They're more about hiring fast enough the right people, not diluting talents. And also the geopolitics that is polluting our space a lot. Now, in terms of technical challenges we have going on, I think we just released, as a few minutes ago, or in a few minutes, a blog post about a latest result where we now have bit flips every hour or so on cat qubits. So I mean, it's kind of playing Dupontis, we're beating our own record at that point, but just because we crossed the target of our graphene device, so we wanted to tick that box. Obviously, the main axis of research for us is on our helium chip, 12 cats, doing a prototype of logical qubits, and we're iterating on that one. Then we have a lot going on the hardware enabling technology parts, where we're not pioneers. We're here to integrate enabling technologies, because the whole point of our approach is really to be fast second. We're not the one requiring the most superconducting qubits. Obviously, Transmon requires way more. So they are pushing enabling technologies in terms of dense wiring, better fabs, those kind of things. So we're just integrating those into our devices. Scaling the fridges, for us, typically 100 logical qubit would fit in a Q2 fridge, for example, so a standard Blue Force fridge. But those are hardware development. They take time. Typically, I think the whole industry is somewhat in the integration hell phase of any serious engineering project. Meaning, we have all those academic demonstrations. They're amazing. We're making a lot of progress. Now we need to put them all together in a machine, and then you realize you made so many silly mistakes in integrating them together, and you debug that. This is exactly what we're doing. And the last aspect we have going on is on the software part, where we have a lot of efforts on the tooling, which is fun with a nascent industry, is that you have to also pioneer your own tools, both for developing and controlling, designing and controlling the system. We open source, for example, the tip of the iceberg of a tooling suite, which is Dynamics, the engine to simulate quantum mechanics efficiently on GPU and do applied machine learning. So yeah, we have a lot going on, both fully internally and in partnership with quite a few academic labs, and scaling the system in our next facility north of Paris, actually not so far from here, where we're integrating all those enabling technologies.
I would like to really second what you said about this integration hell. It's really important to understand that the supply chain to build quantum computers is just not there yet. People have to really grow as well. For example, in our case, laser suppliers, like electronics, fast electronics suppliers, to really be able to put everything together. And that's hard. You have to integrate it, and you have to make to influence the roadmap of the suppliers to make it work. For example, we are also working on photonics integrated circuits, because at some point we believe that free space lasers will reach limitation, and then you have to really make this industry, photonic integrated circuits, at our wavelengths grow to be able to incorporate that in our systems. And it's really the core of it. At Pasqal, we really want to build one unique hardware platform, integrating all those developments that can both serve our clients right now and our partners for use cases, and be good for R&D, for developing new stuff on it, to really accelerate using the same design. You would really need to crack that, and it's very core of our mission to work on this.
It's true that the supply chain has always been a problem, because quantum grow out academia, right? And the problem of academia is that you typically need hardware that works the time of an experiment, right? You don't have 24/7 constraints that come from the HPC world, right? They are used to hardware that runs for years sometimes. And of course, a laser that breaks is in the lab. It's okay. I'll fix it, and but you can't do that in a computer. And it's also true that these computers are systems, right? One of the things, for example, that really amazes me is that the level of control electronics you need to get right, because you need to get everything right, and you have different clocks, right? You have a quantum state clock, but you have got the error correction clock, and all of things are difficult. All of these things are difficult to integrate. How do you How does it work for you, Yuval? Because in your case, I would say it's even more complicated in a way that you are close to Harvard and MIT, and you need to integrate what they do. And so, how does it work for you?
First, the proximity to Harvard and MIT is, I think, one of our biggest competitive advantages. That it's really a bike ride away. And for those that haven't seen Misha Lukin ride his bike on a rainy day and arrive all wet at QuEra, you haven't seen a scientist. The industry is indeed going through a maturity phase. When we launched our computer 3 years ago, we originally had it up for 10 hours a week. We just wanted to see that, first we want to see that someone is using it, and then we wanted to see that we can keep it up. These days, it's up 130 hours a week. So we've gained the experience in maintaining these systems and understanding what's going to break and building telemetry. We use that experience now in deploying a system in Japan, which in our case is really, truly the other side of the world. But it's difficult. It's both. You're right that when an experiment works in Harvard, it could work for 5 minutes on a Tuesday morning when the stars are aligned perfectly. And it's not the same as working 130 hours a week. It's not just about the hardware. A physicist writes software for an experiment, not thinking that in 5 years this software would need to be deployed at a customer site remotely. So there's a lot of, for those that are old enough to know the MacGyver TV series, where it's a lot of MacGyvering going on and changing the engine while the computer is running. But that's part of the fun. One of our recent hires, after we completed the $230 million investment led by Google and SoftBank and now NVIDIA, is to hire a very experienced SVP of engineering that knows how to consistently deliver products, how to outsource the production, how to not, quote unquote, bother the scientists with getting the machine up and getting to this next level of maturity.
So maybe let's talk about timelines a little bit. So Theau, what is your roadmap now? Did it change, by the way, compared to last year? And what is your level of confidence with it?
So indeed, so actually the roadmap did not change yet because we did not yet integrate the latest breakthroughs we've made on our architecture. Typically, for example, last summer we reduced the magic state factory part, so let's say a fourth of the chip by 10x. So reduce a fourth by 10x. And those kind of things need to be integrated and update the whole public roadmap, either to use fewer physical qubits or to have more logical. So we haven't decided yet which path we're going to take. So that's the decision to be made. In terms of timeline, it doesn't really change in the sense that the main bottleneck for us today is no longer research or it's just that if you want to bring up a machine in 2030 that we're just starting to procure each of the component now. When you do the retro planning, you're kind of bottlenecked at that point. So we can't go much faster than that. At that point, we can secure a lot the roadmap and prevent drifts. We can make more on the same timeline, creating more logical qubits. But no, indeed, we can't go much faster than that. Now, in terms of what are the precise steps, so we have helium, 12 qubit chip doing a demonstration of logical qubit. Then we have lithium 48 cats coming up late 26, early 27. Then we'll have beryllium to demonstrate magic state distillation, and then we'll have in 2028, and then we'll have graphene typically. But those are just intermediate step as we integrate those enabling technologies in the process. And also we have to ramp up the fabrication, because I did not answer that part of your question previously, I now realize. Indeed, we used to rely on academic clean rooms. which is great to be extremely capital efficient. But just like any flat sharing, at some point you become too old for that. So we're exactly at that phase. So we're now building our own clean room also, and this will be up and running mid 26. And we'll be scaling to support the integration of more enabling technology within the chip, so through silicon vias, high density wiring, or all that, all those technologies that have been mastered by several of our competitors that we need to integrate as well. So a lot going on that aspect, a lot of hiring as well. If there is anyone interested, do not hesitate for any kind of profiles. And that's the main bottleneck at the moment, because there is actually a lot of room for creativity left in that timeline.
I love when people underestimate their roadmap. So thanks for that. It's always better that way, right? That when you over-deliver, it's always better. I think, Loic, I would like to... So Pasqal is well known for engineering. Actually, I don't know if people in the room know, but Pasqal has not on one, but they have 2 factories already.
Yes, indeed.
So it's kind
Qubits
of...
on both sides of the Atlantic.
I mean, I think we could say you're the quantum computing company that has the most factories in the world, I think.
Yeah, that might be. Yeah.
But it's not, I mean, compared to most of the others. How did you came to that decision of having 2? And how do you, I mean, how are you certain that you can still scan this machine? You mentioned to me that you want to have a modular platform. Is it still the strategy? And this is why you have so many factories?
Yeah, exactly. We've invested a lot of energy, time, and money in making our platform very modular, so that we can scale the R&D individually on each component. And we have our main factory here in France, but we have another one in Quebec, in Sherbrooke. And so actually we are now the largest quantum computing company in Quebec. Not in Canada yet, but it's a relatively large team also with the acquisition of Eponix in Montreal. And we are quite happy to have the first device that has been built in autonomy there in Canada, that is scheduled to be put in operation before the end of this year. So the idea behind this modular platform is really to gain speed and efficiency, to be able to have well-defined interfaces so that teams can focus on really improving each component individually without affecting the others. I think it has been one of the key aspects of our success in deploying machines all around the world with the European machines, but also now that we are preparing for the delivery of the Saudi Aramco machine, which is the first quantum computer bought by a commercially oriented company in the world. So we are very happy about that, but there is also, of course, a lot of pressure in delivering that machine and making it work in an environment that is not really controlled, let's say. So it was very important for us to make this platform robust, reliable. Also, when you want to change parts, you were talking about changing the engine while the machine is running. Well, when you have this modular approach, it's easier. You can really you can provision your inventory in a clever manner, and it works better. So that's really one thing in which we invested a lot, and happy to have that the first results really delivered right now.
So Yuval, you mentioned that you'll have logical qubits very soon, and I think the market can't wait for it. I think the question also for you would be, are you ready to produce a lot of computers? Because then, once you start to have a good technology, there will be 2 questions: how much you can make of them, and to Theau's point, the cost per machine will also be an important factor. Because my clients, they look at ROI, so R is the value of a use case, so usually it's relatively high. But if the I is like very also high, then of course the ratio is not good. So where do you stand on that? So I understand that you will have qubits fast enough, but will you be able to supply the market at cost and at scale also?
So first, just to correct the question, we do have logical qubits. You were asking about 100 logical qubits, and with error correction and a whole bunch of other things. So we're definitely working on that. quantum computers today are not very useful. And because they're not very useful, I mean, they're useful as scientific exploration tools. They're useful to prove the point and to show progress and to provide customers with the confidence that the future is here. I mean, we like to say that quantum computers are moving from one day to day one. So we believe that, but we're getting ready for that ramp up. I mentioned the hiring of our SVP of engineering. So it's no longer the scientists that work on the next generation that have to build machines. So yes, we can build machines and we're delivering them, but our key focus is on continuing to deliver more logical qubits, better algorithms, magic state distillation, another first and another first and another first. Donald Trump would say we get tired of winning, right? But our focus is on the science and on getting the technology to the point where it would make sense to produce very many machines, and we'll be ready by then to do so.
Okay, I think we are finishing on time. I can't thank you enough. I learned a few things today, so thank you for your inputs. I hope that the audience liked it. I think some of the panelists will stay if you have some questions, and of course you can start buying computers.
They are cheap.
Yeah, exactly. Thank you so much.
Thanks, Ed.
Thank you.